method. And we're going to start with a warm-up. So what I'd like you to do, if you take a look, we've got 3 problems here. The first 2 are multiple choice, and the third one is a free response question. I'd like you to pause the audio or pause the whole recording. Take a few minutes, work them out, and then once you're done, go ahead and start the recording up again. All right, so going over the answers, the first question, if f is continuous on the closed interval -3 to 4, differentiable on the open interval -3 to 4, which of the following must be true? Well, continuous on the closed and differentiable on the open to me just yells out mean value theorem, right? So what we know from the mean value theorem is that the slope of the tangent has to equal the slope of the secant at least one value c in that open interval, and so that answer would be choice B. For question 2, if f is a continuous function, f of 6 is -2, f prime is 0, and f double prime is 5. So we have a first derivative that's 0, which means we have a horizontal tangent. A second derivative that's positive, which means the function is concave up. So when we have a horizontal tangent on a concave up function, means we have a relative min, and the min would be at that regular point 6, -2. So we have option D. That's using that second derivative test. Our last problem is a little bit more time consuming. We need to find the relative and absolute extrema for this function. So the first thing I'm going to do is find the first derivative, which is 1/2 minus sine x. If we find our critical numbers, which are the values where sine x equals 1/2, we get x is pi 6 and 5 pi over 6. Now to find the absolute extrema, you're going to want to test your critical numbers and your endpoints. Let's go ahead and do that first. So we have a test.
Just a reminder, staff, the PLC leader meeting will take place in the staff lounge at 2:55. PLC leaders, come on down to the staff lounge for a meeting at 2:55.
All right, got that nice announcement. So there's our 4 values that we're going to test. We test them by plugging them into the original function. F of 0 is 0 plus the cosine of 0. The cosine of 0 is 1. F of 2 pi, well, 1/2 of 2 pi would be pi plus the cosine of 0, which is 1, so you get pi plus 1. F of pi over 6, when you plug it in, you get pi over 12 plus the cosine of pi over 6, which is √3 over 2. And f of 5 pi 6, you get 5 pi over 12, and then plus the cosine of 5 pi over 6, which would be -√3 over 2. So the trick here is to really know exactly what these y values are. Without a calculator, it's a little tricky. Just think of pi as being around 3. So pi over 12 would be, around 1/4. √3 is around 1.8. So √3 over 2 is a number that's a little less than 1, like maybe 0.9. So when you get pi over 12 plus 0.9, so about 1/4 plus 0.9, you get around 1.15, something that's a little bit bigger than 1. So just think of it as being around 1.1, 1.2, something around there. 5 pi over 12, so think of it as 15 over 12. So you're talking about 5/4, so 1 1/4. And then when you subtract something that's around 0.9, so you have 1.25 minus 0.9, so you get about 0.35, 0.4, something around there. So just from looking at this, these are not actual numbers, just think of it as approximation values. So we know then, of course, pi plus 1 is our max, right? Because pi plus 1 is around 4. And our min would actually be the 5 pi 12ths minus root 3 over 2. All right, if we do our relative extrema, so we've got our absolute extrema. So our relative extrema, so we make a sine line. Oops, and make sure you cut it off at the endpoints, 0 to 2 pi. And we put on there pi over 6, 5 pi over 6. This is for f prime. All right, from 0 to pi over 6, the first derivative is actually positive. That's a tricky one to test. I'm going to skip that for a minute and just let you go with that. From pi 6 to 5 pi 6, the easiest number to plug in would be pi halves. So you plug pi halves in, you get 1/2 minus 1, which is a big negative. And then between 5 pi 6 and 2 pi, I would just plug in pi, so you get 1/2 minus 0, which is positive. To know what to plug in between 0 and pi 6, it's not really knowing what to plug in, it's knowing your values of sine. Sine at pi 6 is 1/2, and at 0 it's 0. So anywhere between 0 and pi 6, the value of sine will be something between 0 and 1/2. So when you subtract it from 1/2, you'll still end up with a positive. That's a tricky one. Don't worry, it's not on your test. It's just kind of a little bit of thinking there, right? So we end up with a rel max at pi 6, and then we already found the y value was pi 12ths plus root 3 over 2, because f prime changes from positive to negative. And we have a rel min at 5 pi 6, and the y value would be 5 pi 12ths minus root 3 over 2, because f prime changes from negative to positive. All right, there's your warm-up. So today we're going to learn something called Newton's method, and the basics of Newton's method are really just to approximate zeros of functions. It's a way of finding zeros without using a calculator and without using the actual function. So we've got our little history here. Ooh, who was Newton? He was an English physicist. He's pretty darn well known. He is most known for his works with laws of motion and gravity, and of course the development of calculus. That's kind of a big deal. Very much studied the motion of planets, and was able to completely prove that the planets in our solar system revolve about the sun. A few little tidbits to know about Newton. So how does his method work? Well, let's see if this works on a recording. All right, so we've got Sketchpad coming up. And give it a second. Hopefully it will go. There we go. Okay, so what we're going to do to explain Newton's method is we're going to approximate the zero of this function. It looks like it's at 2, but you never know. So the first thing that you do with Newton's method is you come up with a rough approximation of where you think that zero is. It doesn't have to be perfect. You can, move it around, but so let's just say that we're going to guess that it's around 3, right? We're not sure. We'll put it around there. So if we take the value on the function at that point and actually compute the tangent line through the point of tangency at our first guess, what happens then is it's much easier to find the zero of a line than it is to find the zero of a curve. So we find that tangent line at the point of tangency, and then we graph the tangent line and we take a look, and that the zero of the tangent line actually ends up becoming our next guess. So now we've got another x. We find the y value at that x. We create another tangent line. We see where that one intercepts the x-axis, and that's our next guess. And you continue this process until you are very, very close to the zero. And if you look, each time you repeat the process is called an iteration. So we did 3 iterations, and on our 4th approximation, we actually landed on the actual zero. So you can, and it doesn't even matter, you can start way far off and you'll still, as you repeat the process, so you're just finding the tangent line, find where the tangent line is 0, use that as your next guess. You need to find the next point of tangent C there, find the tangent line, find where that one is 0, use that as your next guess. And you keep repeating that process and you will slowly close in on the 0. So in your homework tonight, there are a lot of problems that look like this one. Use Newton's method to approximate the zeros of f of x equals x to the 5th plus x minus 1 until 2 successive approximations differ by less than 1/10,000th of a point. So you will probably need a calculator to do a lot of this work because there's going to be a lot of decimals involved. But let's just get a start. We'll get a feel for what we're doing here. So the first thing you want to do is start by finding f prime. All right, so one of the things to note is that f prime is always positive. And because of that, we are only going to have 1, 0, either 0 zeros or 1, 0, and it's probably 1, 0. All right, so next we determine an x value where that's kind of close to the 0. And how do you do that? Well, you kind of just do a little trial and error and see if you can find one x that gives you a negative and one x that gives you a positive value, and then pick something in between. So if we try x equals 0, we get an f value of -1, and if we try f of x if we try x equals 1, we get a function value of 1. So something between 0 and 1 would be a place to start. You can actually pick the number, like the actual integer, it's fine. So if we wanted to start at x equals 1, or x equals 0, either way, that's fine. So I'm going to start with my x1 equaling 1. Sometimes in the homework they will give you the first x to start with, and sometimes you'll have to come up with it yourself. All right, so now we want to write the equation of a line tangent to f at our x1 value. So in order to write an equation of a tangent line, we need a point and a slope. So our point, we use the original function, and it's 1, 1. Our slope, we find f prime of 1, so our slope is 6. So our tangent line equation is y minus 1 equals 6 times x minus 1. So now here's the kick. So we have to plug a 0 in for y and solve for that x value, and that becomes our x2. So if we plug in a 0 for y, meaning just get rid of the y, and then you solve for x. So we get, when we divide by 6 and then add 1, so x equals -1/6 plus 1 or 5/6. This now becomes our x sub 2. And that's the next value you're going to use to find your next tangent line. So now we start over again. So we find the tangent line through x2. So our point would be 5, 6. And now is when you're going to want to start using your calculator. So we have 5, 6 raised to the 5th plus 5, 6 minus 1. And we end up with value of 0.2352109. So that's our point. Our slope is 5 times 5, 6 to the 4th plus 1. So we end up with a slope of around 3.411265. So our equation now is y minus 0.2352109 equals 3.411265 times x minus 5/6. Okay, and again, plug in a 0 for y, solve for x. All right, and you end up with okay. Let's see. Oops. So you end up with an x sub 3 that is around negative point. Positive 0.764382. Okay, so 5/6 is actually 0.833. So we're not there yet because we have to be 0.0001 apart from our prior thing. So let's try this one now. So we have a point of 0.764382, and we're going to plug that into our original function. And we get a y value now of 0.02539293. And we know that we're getting close because our y value is getting much closer to 0. And if we plug that into our first derivative, we get a slope of 2.7069156. All right, so we write our equation. Y minus 0.02539293 equals 2.7069156 times x minus 0.764 ... All right, and we solve this again for x. Remember, replace your y with a 0 because we're trying to find where this tangent line equals 0. So we end up with an x sub 4 of around 0.755025. Looks like we're going to have to do it one more time, guys. So our point raised to the 5th. We got 0.0000 is 2.62485556. So our final, let's do our line, we get y minus 0.0003860 equals our slope, just put that down, times x minus our x value. All right, and if we solve for x, remember make your y equal 0, solve for x. All right, and our x of 5 is around 0.754877. All right, you would technically have to keep going. I am not going to because you get the drift of this. When you're doing this tonight, just so you know, if you put your function into y1 and then your derivative function into y2, and then you could just hit trace and type these numbers in each time and get the y values so that you can get the points and the slopes without having to sit there and recompute every single time. So use your calculator to your advantage to help you with all that crazy math, all right? So the next one, Newton's method to approximate the zeros of x cubed minus cosine x until you have two successive approximations that differ by less than 0.0001. So here we go. So the first thing that we've got is we have a function x cubed minus cosine x. And our f prime would be 3x squared plus sine x. All right, so our original function, it looks like the 0 is right around 1. If you think about it, f of 0 is negative. F of 1, you'd have 1, we don't even know what cosine of 1 is, something. Let's do pi halves. Let's do pi. F of pi, pi cubed minus cosine pi, you're way positive, right? I'm just looking at my calculator. I'm in a regular window, and it looks like it's around 1. So I'm going to go with 1. So something between 0 and 2, I'm going with 1. Okay, so we'll make this a little bit cleaner. So we have our first point is 1.045969769. And our first slope is 3.841471. So our first equation is y minus 0.4596. Make sure you get all these decimals because when you have to be that close together, you're going to need all those decimals in order to do it. Plug in a 0 for y. All right, so I get an x value, an x sub 2, of around 0.880358331. All right, next iteration. Dot, dot. So plugging that into my graph. we get a y value of 0.04542989. And a slope of 3.09605595. Write our equation, y minus the y value, and I'm kind of abbreviating here just for time, equals the slope times x minus the x value. Solve for x. So I have negative 0.04542989 divided by 3.09605595 plus 0.88035831. And I get an x sub 3 equal to 0.865684875,919. All right, we're going to do one more iteration and we'll see what that gets us. So moving on to our next point. 0.865 dot dot dot. So plugging that. 865684875. We get 0.00063, and our slope we get 3.00977702. Writing our equation, y minus 0.00063 equals the slope times x minus the 0.865 value. All right, 0 for y, and we solve negative 0.00063 divided by 3.0097702 plus 0.865684875. And we end up with an x sub 4 of around 0.86547555694. All right, we are very close. We are within 2/10,000ths. I'm going with it. So we're very close. If we rounded, we would be close, but not if we rounded both of them. So anyway, good enough. All right, moving on. So how do Newton's method and linear approximation relate? Linear approximation is when you use the tangent line to approximate actual values on the function, whereas Newton's method is used to find zeros. So Newton's method is using tangent lines to find zeros, whereas linear approximation, also called tangent line approximation, is used to actually approximate function values. So the difference between the two, I wanted to show you an example of just a regular tangent line approximation, because on the AP exam you'll see this a lot. It'll say, find the equation of the tangent line and use it to approximate such and such. So here, we're going to find the tangent line approximation of 3.1 to the 4th using a point of tangency of x equals 3. Well, in order to do this, it helps if you have a function. Your function for this, if you look carefully at what you're plugging the number into, the 3.1, it's whatever you're plugging something into, especially if it's a decimal, you're plugging into what looks like x to the 4th. So that's your function. We want a point of tangency at x equals 3. So our point would be 381. We need a slope, so we need f prime. 4x cubed. And our slope at our point of tangency, so again, we're plugging in a 3, so we get 4 times 27, which is 108. So our tangent line equation then is y minus 81 equals 108 times x minus 3. Now, how do we use this for tangent line approximation? We're not trying to find where y is 0. We're trying to find what y is when x is 3.1. So you're actually going to plug here this 3.1 in for x in your tangent line. So you end up with y equals 108 times 3.1 minus 3 plus 81. Just adding the 81 to the other side. So you end up with, that's a 0.1. So you get y equals 10.8 plus 81. And you end up with an approximate value of 91.8. If you actually do 3.1 to the 4th, you get 92.35. So they're pretty close. What it's really saying is if you have the graph of y equals x to the 4th, pretend that that's the graph, y equals x to the 4th, and we want the actual value at 3.1, but we don't know how to really find it. If we use a tangent line, even though we know that the value on the tangent line won't be exactly the same, it'll be pretty close. Let me get a better picture here. So if we have the actual curve, pretend that's our curve, and we have this tangent line, like that, and we want the function value at this point, if we plug into the tangent line instead, we won't get the exact same function value, but we'll get something that's a fairly decent approximation. And that's what tangent line approximation is. It's plugging a value into the tangent line somewhere near the point of tangency to get a fair approximation for what the actual function value is. All right, the special case of Newton's method, approximating the values of roots. So this also works for some other functions. It takes a minute to kind of wrap your brain around it, but we're going to use Newton's method to approximate the square root of 7. So the output of Newton's method is normally x values. It's the x values of the zeros of the function, not the y values. But here we're approximating the square root of 7, which basically is a y value. If we let y equal root x, we don't want to know where x is 7. We want to know what the y value is. So we have to kind of rewrite our function. Instead of using y equals root x as our function, think instead if we squared both sides and thought about y equaling x squared. Now, if y is x squared and we're subtracting here 7 because we have the square root of 7. Think about this then. Whatever number x squared equals would give you the approximation for that root, whatever number your x equals, because we're finding x values. So if x squared equaled 7, that means x would be the square root of 7. Does that make sense? We're trying to find where x squared minus 7 equals 0, which is kind of like saying, hey, where does x squared equal 7, right? So if x squared is 7, then x would be a good approximation for the square root of 7. So we've rewritten our function as x squared minus 7. So just so you know, because you might see this again in the future, if I want to approximate, say, the square root of 13, I would write y equals x squared minus 13, and then use Newton's method in order to find the zeros, and that would give us our approximation. So that's what we're going to do here. So we're going to find the zeros of this function using Newton's method. Okay, so think about something that you think is close to 7. If you think of a perfect square like 9, that would give us an x starting point of 3. So I'm going to use an x1. I'm just going to set it equal to 3. I'm going to use my x1 of 3. So now I need a point and I need a slope. So my function gives me my point. So my point would be 9 minus 7, so it'd be 2, 3, 2. And then I need a y prime. So my y prime is just 2x. So my slope would be 2 times 3, or 6. So my first equation is pretty simple. Y minus 2 equals 6 times x minus 3. Finding zeros, so we cross out the y, we solve for x. So we get x equals, divided by 6, we get negative 1/3 plus 3. So we end up with 2 2/3, or 8/3. Okay, that's our next x value for our next iteration. So we've got 8/3, and I will tell you, let's just do one more iteration just to see if we get a little bit closer. So now we need another point. So we have 8/3, and we do 8/3 squared minus 7, so 64/9 minus 7, so 64.
Yannick Morris to the Math Resource Center. Yannick Morris to the Math Resource Center.
All right, so 7 is 63/9, so 64 minus 63, we get 1/9 as our point. All right, and then our slope would just be 2 times our x value, so 16/3. All right, so we write our equation, y minus 1/9 equals 16/3 times x minus 8/3. And remember to get rid of the y because y is going to 0. So our x3 would be negative 1/9. I'm going to rewrite it like this. Negative 1/9 times 3/16 plus 8/3. And doing a little bit of crisscross here. So we end up with negative 1/48 plus 8/3, so times 16. Plus 128/48. So we end up with a final approximation after 2 iterations of 127/48. If you do 127 divided by 48 in your calculator, you get a value of around 2.646. And just out of curiosity, let's check what the square root of 7 is. Square root of 7 is around 2.64. This one was 2.6458, and this is 2.64575. So we were actually very close. I mean, we were close to 6.458. We were close all the way out to 4 decimals, and if you rounded, we were as close out to the nearest 10,000. So, and that was just with 2 iterations, so it worked really well. So sometimes Newton's method works really clean, really simple, and it works pretty easily, and sometimes it gets a little messy. All right, one last thing you need to know is that Newton's method does not always work. Sometimes the zeros of the tangent lines just don't converge. This can be for a variety of reasons. So I'm going to show you what it looks like when the zeros don't converge. We're going to look at x to the 1/3. All right, let's try this again. All right, I'm going to clear this off. show you what it looks like. So if you graph y equals x to the 1/3, so x to the 1/3 looks something like this. And the problem is, if you draw a tangent line at, say we're trying to find the 0, we can see the 0, right? It's not too hard, it's at 0. So, but if we go out and we draw a tangent line, say we get close here. And so this is our new x value, and there's our new y value. What ends up happening is the repeated iterations actually take you further and further away from the 0. So what that's saying is that the zeros, when you do the iterations of Newton's method, they don't converge. They don't get closer to 0. They actually get further away from 0. So be careful, because some of your homework problems tonight, Newton's method won't work. The numbers won't go down. They'll actually go up, and they'll get further and further away from each other. And they will ask you in the problems to just be aware of that and mention when that happens. So I wish you luck. It's a lot of decimals today. Just be aware that you can put everything into your calculator and use that calculator to help you find all of these y values and all of these slopes. Try to write neatly, write neater than I do. I know that I get kind of messy, and just do your best with it. But remember, it's all it is just repeatedly finding tangent lines, putting a 0 in for y and solving for x, then finding the next tangent line, putting in a 0 for y and solving for x, and doing that over and over and over. All right, good luck, guys, and I will see you tomorrow.